Okay, here's the technique then, and that's the technique you follow, and if you're asked to do one of these in the exam, that's what you do. 3-step program, form the auxiliary equation, and we'll talk about that in a second. It's a quadratic equation if it's a second order differential equation. Then we solve that quadratic equation, that auxiliary equation, and choose the correct form for the solution, and on your data sheet you will have those forms that we're going to choose, so we'll look at those in a second. And then finally, given boundary conditions, initial conditions, we can find values for the constants in this solution. So that's what we're going to do, follow this technique. So let's look at an example. This is the table of solutions, and we'll come back and look at that when we've solved our first example. So example number 1, which I think you've got in your notes. There's a second order differential equation. So it could be like the one that we've got, that we had at the beginning, this model here. Right. So it could be an example if we look back at the model we had where the mass was 4, eta is the term in front of the dx by dt. So in this particular example, eta is 12, and finally the last one is minus x, the spring constant's minus x. So we'll look at this as an example and see what solution we get. So looking at this then, before we start, let's look at this, and it's not always going to relate back to the example we've talked about, but I will relate it back to this model that we were thinking about with the mass and the spring constant and the viscosity of the liquid. Note that the right hand side is 0. It's always going to be 0. If it isn't, we need to make it 0, and if we can't use this method to solve it. We'd have to think again. But the examples you are going to come across the right hand side will be 0. Let's think for a minute about these boundary conditions in terms of our model. What we need is a situation when t equals 0. What we're saying is, for our model, x equals 3. So the initial displacement from 0 is 3 in this particular model. And when t equals 0, the thing's moving with a velocity. dx by dt has a value, 2. So if we go back to this, it sort of applies to this, look. What's the initial displacement when time equals 0? 3. And what's happening to the thing at this point? It's moving with a velocity, so the gradient of the curve at that point would have a value. So if the situation was when x equals 0, the velocity is 0, then it would probably be peaking at that point because the velocity would be 0. So we're given some initial conditions, and then we can solve it. So what we do now is follow these steps. So we've got these 3 steps, 1, 2, 3, and we're just going to follow them to solve this. And it's quite straightforward once you've done 1 or 2. Hopefully you'll see that. What is this n? We let n represent the differential, and we form a quadratic equation that we call the auxiliary equation. What all that means is, I look at this differential equation, wherever it says dx by dt, I replace that with m. And so, because that's the second differential, I replace it with m squared. And dx by dt here, the first differential, I replace with m. And so I write down 4m squared plus 12m minus 8 equals 0. And that's my auxiliary equation. So there's nothing to do. Well, how do you spell auxiliary? 1L. Equation. So there's nothing to do, it's just literally write it down, replace the differential with m. So it looks like a quadratic equation, and then we solve it. Well, there's no differential in the 8, so there's no m, so it's just a number. Yeah. Now we solve it. We can try and tidy it up. Often we can divide by a number to try and make it more straightforward. If we look at this, if the right hand side is 0, and it always will be 0, I can multiply or divide by anything I like. So if I divided both sides by 4, I'd get rid of that 4 there. This would become 3, and that would become 2. So straight away I can write, dividing by 4, m squared plus 3m minus 2 equals 0. Okay, now we've got to solve it, and we've got 3 ways to do it. One way is just to look at it and factorise it. One way is to use the perfect square that we talked a bit about last week, form a perfect square, or, which is an extension of that perfect square method, just use the quadratic formula. That will always work, the quadratic formula. Okay? But it's worth having a look at it. I always look and say, are there two numbers that add together to give 3 and multiply together to give minus 2? Yeah, add together to give 3 and multiply together to give minus 2. So there isn't an obvious one. Let's use the quadratic formula. X equals minus b plus or minus the square root b squared minus 4ac all over 2a. Is it on your formula sheet, the quadratic formula? Yes, so you don't even need to remember it, okay? But you do need to be able to use it. So then we plug in our values. A equals 1, the number in front of m is just 1. B equals 3, and C equals minus 2. So we put those values in and work out what x is. So if I just pause this, you can have a go at it. So using the quadratic formula we get this. Try to do this in one hit on the calculator, and then just change the plus to a minus. The other way we could do it is using the perfect square. So what we do is we take this m squared plus 3m minus 2 equals 0. We halve the 3 and square it, and that gives us 2.25. So the perfect square would be m plus 1.5 squared, which is plus 2.25, but then we take away 4.25 and we get back to 2, we get minus 2, so we end up with that. So written like that, we can say m plus 1.5 squared equals 4.25. So square rooting both sides equals plus or minus, and that's where the plus or minus comes in, the square root of 4.25. So m must equal plus or minus the square root of 4.25 minus 1.5. And if we work out what that is, we should get the same answer. And we get the same answers. I don't mind which way you use. You know, if you like that perfect square method, then use it. You're probably more used to the quadratic formula method, though. And I don't, you know, so long as you get the roots, that's the truth. So we've solved it, and we've got m equals 0.56 or minus 3.56. Now what we do is we go to step 2 and choose the correct form for the solution. So that's where our table comes in. If we look at your table of solutions, it looks a bit like this. If your roots are real and different, so I've got 2 values, then it's this solution here, this one. So I've got 2 separate values for k1 and k2, 2 real numbers, That means this is the solution. The solution has the form y equals ae to the k1 x plus be to the k2 x. That's what our solution looks like. And you get this solution if the square root is positive. So if we look at our example, this is going to work because when I work out this bit, and this is the key part of our function of our quadratic, if that's positive, I'm going to get a real answer, aren't I? Do you remember when we were thinking about imaginary numbers, your answer was complex if this turned out to be negative, and you had to introduce the imaginary number j. So if this is positive, which it is in this case, then we're after the case where we've got two real and different values here, k1 and k2. So we're using this one. So when you solve your quadratic and this is positive, you know you're looking for this solution. So I can write now my solution. It's of the form y equals ae to the k1x plus be to the k2x. So I can go back to my example and say, therefore, I have two real and different solutions and there they are, 0.56 or minus 3.56, so therefore y equals ae to the k1 x plus be to the k2 x, where x is our variable. So in this case, so I just have to talk through this bit. So we've got two real and different solutions, so it gives us this solution. So in this particular case, dependent variable is x, not y, going back to the beginning here. The dependent variable is x and the independent variable is t. So we write this. X equals ae to the 0.56 t plus be to the minus 3.56 t. Now we need to put in the boundary conditions and work out what a and b are. So I'll stop this video here and we'll look at that.